Okay, in this video we're going to do a quick refresher on how to deal with constant conditions when you're talking about gas laws. And what I mean by constant conditions is we have a volume measurement, or we have a pressure measurement, or we have a temperature measurement, but nothing's changing. So the temperature's not rising, the volume's not increasing, the pressure's not falling, we don't have anything going up or down, but we do happen to have those measurements. And there's a formula we've been using called the ideal gas law that relates all of these measurements to each other. It's kind of cool because if you have the pressure and the temperature, you can always figure out what the volume ought to be. Or if you have the pressure and the volume, you know what temperature that's happening at. The two measurements are an indication of the third, as long as we get all the units correct and we organize it right. So we're going to go through some of the basic mechanics here. All right, so the first thing I want you to recognize is what these mean. Obviously that's pressure, but it must be in atmospheres. Okay? This is a very picky gas law in that you can't just throw in any units you want, because then you would need a different constant each time. So if we're going to make this work, we need pressure to be in atmospheres, we need volume to be in liters, okay? So they have to be in these units. Temperature has to be in Kelvin as usual. N represents the number of moles of whatever gas. So it's like how many particles are bouncing around. It doesn't really matter what they're made of, it's how many of them are bouncing around in this sample. And then R is the ideal gas constant of 0.0821. We talked about this in class. That has units of liters, atmospheres over moles, and Kelvin. I don't want you to get hung up too much on what that fraction right there means. All I want you to know is how to work with it. What this is telling us is for this gas constant to actually make all these things be very accurate, we have to use these measurements in it. And when you do all your math, all these units cancel out except for the one you're looking for. So the short story of this is these are the units necessary to make all this stuff work. So this constant dictates what these other things must be in. They must be in those 4 units. Okay? If I have something in milliliters, it doesn't match the units that are in that constant, and I get something that doesn't mean what I think it should mean. So those are requirements. You have to have those. But this is actually pretty easy to set up. Okay, I got 40 grams of nitrogen. I got a pressure of 600 torr, and I got a temperature of 30 degrees Celsius. And all I'm trying to do is analyze the volume. So I'm going to list out what I have. P, V, N, R, T. Okay, so just like the other gas law, we're going to try to organize all of our data into a nice little list where we can see it. Okay, so the pressure here is 600 torr. The volume, we don't know. We're looking for that. N is number of moles. I don't have number of moles, but I do have grams, and I know what it is. So I'm going to write down 40 grams of nitrogen. I got an R value of 0.0821, and I'm not going to bother writing the units over there right now because just like before, I'm going to get all the units to match these things before I start, and then I don't have to really worry about unit cancellation. I know my algebra is going to take care of it. My temperature is 30 degrees Celsius. Okay. So I got my list of measurements. They need to match these units. So I'm going to do a little work on this before I actually calculate anything. All right, let's take a look at pressure. It's in torr. It needs to be in atmospheres. So I'm going to do a pressure conversion from torr to atmospheres. I'm going to cancel torr out so it goes on the bottom, and then I look up my values. 1 atmosphere is 760 torr. So I'm going to grab a calculator. That's going to be a decimal. We'll round it off a little bit, but that's going to be our general pressure. So 600 divided by 760. I get 0.789. I'm just going to round that to 0.79. All right? 0.79 atmospheres. Make sure you write down units and you keep track of where you're at so you get things all the way they need to be. All right, let's take a look at what else we have to work with. This should be in moles, and I have grams of nitrogen. So I need to turn it to moles, which is something you've done 1,000 times. I'm going to look at the periodic table and find the molar mass. 1 mole is what the periodic table shows us every time. And 1 mole of nitrogen is 14 times 2, which would be 28 grams. So I need to take 40 divided by 28 to tell me how many moles of nitrogen molecules are bouncing around in that sample. 40 divided by 28, I get 1.43. 1.43 moles, okay? So now my N is in number of moles. I got that taken care of. R is a constant. It won't change. It's got a bunch of units that go with it. They're written right over there, but I'm not going to put them here just to keep from cluttering it up. And then my last one's temperature. You know that no matter what, when we're dealing with gases, temperature has got to be in Kelvin. So I'm going to add 273 to that, and I get 303 Kelvin. So now I got everything where it needs to be. All I'm going to do is plug that in and solve for the one I'm looking for. I'm looking for V. Okay, now you could also do this by solving before you actually plug the numbers in. Here's what I mean. PV equals nRT. If I want to get V by itself, all I have to do is move P to the other side by dividing. I divide both sides by P and I get volume equals nRT over P. I did that implicitly with the variables there. You can do that with the numbers there. It doesn't matter as long as you at some point divide by P. So I'm going to put all that stuff in here. Okay. On top I have N, R, and T. N is 1.43. R is 0.0821. Don't forget that zero. If you miss that zero, your answer is going to be 10 times different than you think it should be. And then the temperature is 303. I'm going to put the pressure on the bottom, which is 0.79 atmospheres. Now notice I didn't write any units up there. Technically I should, but I've already done all the unit work over here. I know everything's set up the way it should be, so I'm just going to throw the numbers in to make it a little simpler. Okay. Type all that in, and we should get a reasonable looking volume. So I got 1.43 times 0.0821 times 303 divided by 0.79, and I get 45. So I get a volume of 45. Now, what does 45 mean? Well, I know that volume here for all these to work out must be in liters for that constant to be something I work with, so this would be 45 liters. That's quite a big volume, but let's take a look at what that means. Okay, 45 liters. Now you guys know that 1 mole of any gas at STP is going to take up 22.4 liters of space. This is about double that. Okay, I have 1.5 moles roughly. Okay, so how can it be double the volume, but only 1.5 in terms of the number of moles? Well, look at the other conditions. The pressure went down a little bit, actually substantially, where there's a lot less pressure squeezing on it, and the temperature went up. Both of those together are going to create a situation where this gas is going to expand more than ordinary. So certainly more than at STP. So 45 liters, it seems like it fits. It's about right. Okay. And that's using the ideal gas law to solve a problem.